Gauss-Jordan elimination is an algebra method for solving systems of equations. So in this particular example I'm about to apply it to, I have three equations and I have three variables. So x, y, and z are my three variables, and 1, 2, 3 equations there. So what those things are and why we're doing this is that this and this and this are all Cartesian equations of planes. So if I could solve the values of x, y, and z that were true under this situation, and this situation, I would have found the place where all three of those planes intersect. And we're not going to worry about that quite right now. We're just going to do the algebra technique to make it happen. But presumably there is this one is a sheet like this one is a sheet like this, and this one is a sheet going crosswise, and they will all come together in a single point somewhere in space. So we need to try and figure out how to get that. You've done the elimination method before when you were in grade 10. You would stack two equations on top of each other, scale the bottom one up so that you could eliminate the x's or eliminate the y's or eliminate the z's. You did that for finding the intersection of lines. So this is similar, except that there are three variables. And what we're going to do is use a thing called a matrix so that I don't have to write the x's, the y's, or the z's anymore. So what I'm going to do is I'm going to draw a great big square bracket like this. And all I'm going to write in this bracket are the coefficients on each variable. So instead of writing 2x, I'm just going to write the 2. Instead of writing 4y, I'm just going to write 4. Instead of negative 3z, it's just negative 3. And then 29 here. I've got a 1, a negative 2, a 4, a negative 21, a 3, a negative 6, a negative 1, and a 2. And I'm going to put a line in there for those equal signs. Okay, so why does this help me, you're asking? Well, anything that's in this column is a coefficient attached to an x. And the fact that it's attached to an x is implied by the fact that it's in that column. So I don't have to write the x's anymore. I just know that these numbers are here. And that when I drop out of the matrix, right, I just have to attach the letters back on. So it's going to save me some space. It's also going to let me manage more than one variable at a time, which is super handy when you get into 3 or 4 or 5 variable systems. To be able to just do it in one place. So the basic rules here are the same as rules for the elimination method. Number 1, you can scale up any line by any amount. Scale up any line by multiplying all terms. So if you go and you look over at that example, I would like you to look at the numbers on the x's. Now, I want to try and get matches here, right? 2 and 1 are not the same number, 1 and 3 are not the same number, and 2 and 3 are not the same number. But I could fix that. I could make these two numbers match if I doubled this middle row. So what I'm going to do in my next line, draw my matrix. In this row, right at the beginning, I'm just going to keep row 1 just as it is. In this row, I'm going to put in twice row 2. And in this row, I'm going to leave row 3. Now, if you just leave these little instructions for yourself at the side, you'll be able to track what you've done. So when it comes time to check your work, or if you do find you've made an error somehow, you can see what you did in each step. So if I were to actually execute this, row 1 was just 2, 4, negative 3, 29. Twice row 1 would be 2, negative 4, 8, negative 42. R3 was just 3, negative 6, negative 1, 2. Alright, which brings us to the second thing that we can do during Gauss-Jordan elimination is you can add or subtract any two rows together. Any two rows. Okay, so in my next line here, I'm going to keep row 1, and then I'm going to do row 1, subtract row 2. And I'm going to keep row 3. So row 1 was 2, 4, negative 3, 29. Row 1 minus row 2, so 2 minus 2 is gone. 4 minus negative 4 is 8. Negative 3 subtract 8 is negative 11. And 29 subtract negative 42 is 71. 71. Row 3 down here is 3, negative 6, negative 1, 2. Okay, so how has that helped us? Well, in this row, if I were to drop this out of the matrix, that says no x's plus 8 y's minus 11 z's equals 71. 71. And 0 x's I don't even need to write. So do you notice that I've eliminated a variable? So that's very handy because now I only have 2 letters left. If I could keep working at this and eliminate another variable in this row, I would end up with a solution for x or y or z, depending on which number is left. So that's the plan. And I'm just going to keep working on it until I can get to what I'm after. So I'm going to, let's see, what can I do to this? I am going to take row 3 and subtract row 1. I'm going to do that in this line. I'm going to keep row 2 right where it is, and then I'm going to keep row 3 right where it is. So row 3 minus row 1, 3 minus 2 would be 1, negative 6 minus 4 is negative 10, negative 1 subtract negative 3 is 2, and 2 subtract 29 is negative 27. And I have 0, 8, negative 11, 71, and 3, negative 6, negative 1, and 2. Alright, so why did I do that? Well, do you notice that instead of having a 2 in front, I now have a 1 in this position? Which means if I triple this row, I will have a match for this x here. So I'm just making these tiny little manipulations to the equations as I go along and systematically eliminating everything but one x, and then eliminating everything but one y, and then eliminating everything but one z. That's the plan. So in that vein, I'm going to continue this by tripling row 1. So 3 row 1s, keep row 2 where it is, and keep row 3 where it is. So tripling this would be 3, negative 30, 6, 60, 81, 11 and 71. 3, negative 6, negative 1, 2. Okay. So now that I have a match in the x's, I'm going to scale this back down. So I'm going to put in a third of row 1. I'm going to keep row 2, and I'm going to do R3 minus R1. So that will eliminate the x here. So a third of this would be whatever I had down here. 1, negative 10 to negative 27. Row 2 is 0, 8, negative 11, 71. And then 3 minus 3 is gone. Negative 6 subtract negative 30. That would be 24. Negative 1 subtract 6 is negative 7. And 2 subtract negative 81 would be 83. So I have successfully eliminated the x from 2 of my rows. Now that I've eliminated the x's from 2 rows, I'm going to try and start eliminating the y's from what's left here. So do you notice that if I tripled row 2, I would have a match, right? 3 times 8 is 24. So that's what I'm going to do in my next line. I'm going to keep R1. I'm going to triple R2, and then I'll keep R3. So 1, negative 10, 2, negative 27, 0, triple 20 or 8 is 24, triple 11 is negative 33, triple that is 213. 3 times 7 is 21. So 220. Yep. 0, 24, negative 7, 83. Okay. So I'm going to keep R1. I'm going to go back to 1/3 of R2, and then I'm going to do R2. No, I'm going to do R3 subtract R2. I'm choosing that because I'll end up with a positive number if I do it in that order. So 1, negative 10, 2, negative 27. So we're reverting to 1/3 of row 2 here. So a third of 0 is 0. A third of 24 is 8. So that is negative 11. And a third of 213 was 71. And to do R3 minus R2, 0 minus 0 is gone. 24 minus 24 is gone. Negative 7 subtract negative 33 is 26. And 83 minus 213 is negative 130. Okay. So this is the point where you jump out of this matrix. Because if you look at this row, in equation format, that says 26 z's. It's a z because it's in that third column, equals negative 130. So z then is negative 130 over 26, and that is negative 5. So I've just figured out that the z value that makes all 3 of those equations true is negative 5. Now I just need to get the y's and the x. So I can do that by lifting this line out of the matrix. So I'm going to pop it up here. Let's see. 8y subtract 11 z's. But I know that z is worth negative 5. So in it goes. equals 71. So 8y's plus 55 is 71. 8y's is 71 subtract 55. 8y's would be 16. So y equals 16 divided by 8, which is 2. So if I use a -5 for x and or -5 for z, sorry, and a 2 for y in all of these three equations, it works. Now I just need the x value. So I'm going to take this top line here, 1x minus 10y's, but y is worth 2, plus 2z's, but z is worth -5, is equal to -27. So 1x, that's minus 20. This is minus 10 equals -27. 1x minus 30 equals -27. Pop that over. So x is -27 plus 30 is 3. So after all of that, I've discovered that if you use the point 3, 2, -5 in all three of these equations, that all three of them will work. So just to check that, in this one, 2 times 3 would be 6. 2 times 4 would be 8. And -5 times -3 would be 15. And if I added all those up, 6 and 8 is 14. 14 plus 15 is 29. That's neat. Put the 3 here. 1 times 3 is 3. 2 times -2 is -4. -5 times 4 is -20. 3 minus 4 is -1. -1 subtract 20 is -21. That's a match. And 3 times 3 would be 9. 2 times -6 is -12. -5 times -1 is +5. 9 and 5 is 14. 14 minus 12 is 2. You get another match. So I was able to use elimination method in order to find the point of intersection between these three planes. And you might be looking at all that and saying, that didn't save me any time. Well, and my answer to that is, I only did one step at a time. And the real power of this is it lets you change all three rows in one step, if you like, if you're good at it. So after more practice, you should be able to get through this in reasonably short order. So I'm going to erase this, and then I'm going to do it doing multiple steps at a time. We're going to come up with the same answer, hopefully, assuming I don't make any errors, so that you can see how few matrices are necessary to actually get to the answer. Alright, so I'm going to add one more rule up here. Number 3, you can switch the location of any row. Switch the location of rows. So when I look at this matrix, I see a leading coefficient of 1 in the front. I'm going to use that 1 to eliminate the x up here and to eliminate the x down there. That will leave a 1 behind. So I like this row. This is a keeper. I'm going to put it at the top of my matrix, row 1. Then I'm going to take 2 of that row and I'm going to subtract row 1. Sorry, it's row 2. 2 of row 2, subtract row 1, and then I'm going to take 3 of row 2 and subtract row 3. So you notice that I've done 3 operations there in one matrix transition. So my second row was 1, -2, 4, -21. So in it goes. So now I need to take 2 of these and subtract 1 of those. So 2 times 1 is 2. 2 minus 2 is gone. 2 of these is negative 4. Negative 4 minus 4 is negative 8. 2 of these would be 8. 8 subtract negative 3 is 11. 2 of these would be negative 42. Negative 42 subtract 29 would be negative 62. Negative 71. Now I need to take 3 of these and subtract 1 of these. So 3 of these would be 3. 3 minus 3 is gone. 3 of these would be negative 6. Negative 6 subtract negative 6 is gone. 3 of these would be 12. 12 minus 1 of these would be 13. 3 of these would be 63, negative 63. Negative 63 subtract 2 of those would be negative 65. And in one go, I eliminated everything except the z. So by using this method, I was able to get all that work done in just one matrix. So I spot here then that 13z is negative 65. So z is negative 65 over 13, which is negative 5, as we predicted before. So I'm not going to get the rest of the letters because it's going to look exactly the same as it did over here, like when we did it the first time. So if you get good at this and you can sort of predict what's going to happen in the matrix, then you can get this all done in just one go, which is very handy. It's very quick. So the purpose of this assignment is just to practice this technique and see if you can wrap your brain around it. Some tricks. You notice that I always eliminated the things in the first row first. So once I had eliminated my x, then I started trying to eliminate y's. And once I eliminated y's, then there'd just be a z equals left over. That's the pattern you want to try and replicate. Alright, so I'm going to erase this and we'll try one more example, and then I think you're ready for the practice problems. Alright, so I'm going to drop this thing into my coefficient matrix. So I've got 3 planes here. I want to find where they intersect. So my x values are 3, negative 6, and 12. Y's are negative 10, 15, and negative 5. Z's are 4, 12, and 8. And the things on the other side of the equal sign are 1, 1, and 12. So in the spirit of following these 3 rules in order to eliminate 2 of the x's and then 1 of the y's. Oh, sorry, it's negative 8 there. So I'm going to keep my first row because it has the smallest value for x in it. And then I'm going to double that row to row 1 and add row 2. 6 plus negative 6 would be gone. And then for this one, I'm going to do 4 of row 1 and subtract row 3. So if I just keep this here, 3, negative 10, 4, 1. 2 of these is 6, 6 and negative 6 is gone. Negative 20 and 15 is negative 5. 8 and 12 would be 20. 2 and 1 would be 3. 4 of these is 12. 12 minus 12 is gone. 4 of these is negative 40. Negative 40 subtract negative 5 is negative 35. 4 of these is 16. 16 subtract negative 8 is 24. And 4 of these would be 4 minus 12 would be negative 8. 4 of those subtract 12 is negative 8. Yep, perfect. Okay, so I've successfully eliminated x from 2 rows of this matrix. I'm going to work on those 2 rows then to try and eliminate y. So I'm just going to keep row 1 as it is. I'm going to keep row 2 as it is. And in this row, if I took 7 of these subtract that one, I would get a 0 again. So 7 row 2 subtract row 3. So I've got 3, negative 10, 4, and 1 just hanging around. And I have 0 and negative 5, 20, and 3 just hanging around. and those are gone. 7 of these would be negative 35, subtract negative 35 is gone. 7 of these is 140, subtract 24 would be 116. 16, yep. And 7 of these is 21. 21 subtract negative 8 would be 29. Alright, now that looks kind of gross. But this row here says that 116 z's equals 29. Alright, so z would be 29 over 116, which looks like a horrendous fraction. But if you type that into your calculator, clear 29 divided by 116 is a quarter. So I found out that the z value that works there is 1/4. Now I have a choice. I can try and dump this fraction into this row of the equation and then get something which may itself be a fraction and dump it into the top one. I could do that. Or I could stick with the matrix. So what I'm going to do then is I'm going to use, I'm going to try and use this negative 5 to eliminate the negative 10. And the reason that's a good choice is that there's no x value here. So it's not going to reintroduce any changes in my x. So I'm going to just continue with this just for fun. Instead of row 1, I'm going to do row 1, subtract 2 of row 5. 5. There are 3 rows in this matrix. Row 3, row 2, that row, whatever row that is. Then I'm going to keep row 2 all on its own, and then I'm going to divide this whole mess by 29 so I can get it down to a reasonable looking row. Alright, so R1 minus 2 of these. 3 minus 2 nothings is just 3. Negative 10 subtract negative 10 would be gone. And 4 subtract 40 would be negative 36. One subtract 6 would be negative 7. Let me just make sure that's right. Negative 2 of these would be 10 plus 10 is gone. Negative 2 of these is negative 40 plus 4 is negative 6. Negative 6 and 1. Check that there. That would be negative 5. Okay. Row 2 was 0, negative 5, 20, and 3. And this row is 0, 0, 4, 1. Alright. Good. So, where is this going, you may ask? Well, now that I've eliminated the y from this and the x from that, there's only z's kicking around that I need to get rid of. So I'm going to take row 1 and I'm going to add 9 of these. And I'm going to take row 2 and I'm going to subtract 5 of them. I'm going to leave row 3 alone. So 9 of these plus 3 is 3. 9 of these plus 0 is 0. 9 times 4 is 36. Plus 36 is gone. 9 of these would be 9, and negative 5 would be 4. Okay. 5 of these are, so this minus 5 of those is gone. Negative 5 minus 5 of those is negative 5. 20 subtract negative 20, or subtract 20 would be 0. And then negative 5 of these would be negative 5. And 3 would be negative 2. Let's just check that. 3 minus minus 5 is -2, 20 minus 20 is gone, -5. Yep. Okay. And then this row would be 0, 0, 4, 1. Now, if you look at what I've got there, my top row says 3x equals 4. Therefore, x is 4/3. -5y equals -2. Therefore, y is 2/5. And 4z equals 1. Therefore, z equals 1/4. So that's an answer. It's an ugly answer, but it's an answer. All three of them were fractions. And what's neat is, by staying in the matrix, do you notice that the fraction didn't occur until the very last step? And I didn't have to do any common denominators. I didn't have to do any of those funny addition rules or multiplication rules for fractions. I just kept it in the matrix until it spat out 3 of these is worth 4, -5 of these is worth -2, and 4 of these is worth 1, and then got the fractions that way. So if you can figure out how to do this, not only is it faster once you're able to do multiple operations per step, but it can spit out these ugly fraction answers without ever having to actually use fractions in the process. So give the practice questions a try and see how it goes.